Hi, in this video, I'm going to talk about the concept of surface tension and capillary rise. Okay, this is a part of chapter 2 of our course on groundwater hydrology. So what is the surface tension? At the interface between two immiscible fluids, for example, water and oil, or water and air, the molecules that are located at the interface, they are exposed to different forces compared to the molecules that are inside the bulk fluid. For example, look at these two molecules. This one is at the interface, and this one is in the bulk liquid, right? As you can see, the one at the interface, they are subjected to a net force toward the interior, okay, while the interior of the fluid. But the one that are in the bulk liquid, they are actually attracted to each other equally. So the apparent physical consequence of this unbalanced forces at the interface is to formation or is to create a hypothetical skin or membrane, right, at the interface between the two immiscible fluids. Okay, and this is this hypothetical skin that makes basically make it possible for the insect basically to sit on water. Or for example, if you do it gently, you can place a clips on water. Okay. So here there is a definition that is the intensity of the fluid attraction per unit length at this along this interface is called surface tension. Okay, so the intensity of fluid attraction per unit length along the interface is called surface tension. Okay, so what is capillary rise? I guess maybe you have already seen that in your I don't know, physics or chemistry courses, but when a small cylindrical glass tube called capillary is dipped in free water, a meniscus is formed as a result of the contact angle theta between water and the solid wall. So this is the meniscus here, formed here, and this is as a result of the contact angle between the liquid and the solid wall. So what is the contact angle? The contact angle is actually the angle at which a liquid gas interface, so here the blue is the liquid, that's white is the gas here, and that is the interface between liquid and gas interface, meets the solid surface. This is the solid surface, and this theta will be the contact angle. Okay, so basically contact angle is a quantitative measure of wetting of a solid by liquid. Okay, so so if the adhesive force between the liquid and the solid surface, so the adhesive force between the liquid and the solid surface is more than the cohesive force between the the molecules in the bulk fluid, the fluid prefers or likes to wet the surface. So we call the surface wettable, right? With respect to that particular fluid. Okay, and in that case, the contact angle will be very small or zero if the surface is completely wettable. Okay, but if the cohesive forces between the molecules in the bulk fluid is more than the adhesive force between the fluid and the solid, right, then the surface will be not wettable. Okay, compared to that particular fluid, and you will be dealing with the large values of contact angle. Okay, so in the case of this picture here, if the adhesive force between the fluid and the surface, right, is more than the cohesive force within between the molecules within this bulk liquid, the fluid basically wet the surface and it rises above the water reservoir. Okay, so the question here is how to estimate this capillary rise that is represented by the parameter h here. Okay, and the radius of this tube is r, or the diameter is 2r, and this theta is the contact angle. Okay, so so basically, let me read it from here. The height of capillary rise h can be calculated by considering the surface tension, which we discussed in the at the beginning of this video, sigma, and the contact angle theta between the fluid and solid. Okay, so how can you do that? So if you dip this capillary tube basically in this free water, you have this capillary rise, and let's just consider this parcel of fluid. Okay, you bring it here. So there are two forces acting on this parcel of fluid in a vertical direction. One is the weight of the fluid, that is m times g, and m, the mass, is equal to density rho times v. So that is rho times V. The volume here, this is a cylindrical volume, that is pi r2, the area, times h, that is the height. So that will be volume. Pi r2 h is the volume of that cylinder times density. That gives you the mass, and you multiply it by g to get the weight. Okay, that's the gravity force. And then the upward force is the sigma, that is the force per unit length, and the perimeter of this interface is the perimeter of a circle, that is 2 pi r. So the force will be sigma times 2 pi r. Okay, so in the vertical direction, at equilibrium in the vertical direction, these two vertical forces should balance each other. So therefore, the downward rho g h times pi r2, that is basically this term here, should be equal to 2 pi r times sigma, that is 2 pi r times sigma, times cosine theta, because you're considering the vertical component of the forces, right? Times cosine theta, okay? And this is a little algebra here, then you can calculate h as equal to 2 sigma over rho gr times cosine theta. And sigma is the surface tension, rho is the density of the fluid, g is the gravity acceleration of gravity acceleration, and r is the radius of this capillary tube, theta is the contact angle, and h is the capillary rise. Okay, and that's the way you can calculate the height of the capillary rise. Okay, so there is a so here, based on this equation, you can already see that the capillary rise basically decreases, decreases when you're dealing with the large, when you're dealing with the basically larger capillary. Or in other words, you can say it increases when you're dealing with the thinner capillary. As R gets smaller, the H value will be bigger and bigger. Okay, because they're inversely proportional. And here you can see you have this as you reduce the radius, basically R, the H basically is increasing. Okay. And for pure water in killing glass, and here killing glass basically is a keyword for contact angle 0. Okay, so pure water, so you know the density of the at 20 degrees. So you know the density of the water at 20 degrees, you know the surface tension at 20 degrees that is given here, you know the gravity, right? And since it's killing glass, then the cosine theta is 0, therefore cosine 0 is equal to 1, so that will be out as well. So then you can plug basically these values into this equation, and then this equation will be simplified to H is equal to 0.15 divided by R, when R is expressed in centimeter, and H as well will be in centimeter. Okay, so this is as well a common equation used, especially in the kind of a hydrology textbook, because you're mainly dealing with water, right? And these parameters are all given, so you can have a simpler equation. So for pure water in killing glass, theta equal to 0, and at 20 degree, sigma is given, rho is given, that is 1 gram per cubic centimeter, so that for R in centimeter, the capillary rise in centimeter is equal to that one. So that is about the capillary rise. There's an example here. I'm going to solve this example, and that will conclude our video on capillary rise. That is an open killing glass tube. Remember, when you say killing glass tube, that means theta is equal to 0, is inserted vertically into a pan of water. What tube diameter is needed if the water level in the tube is to rise 1 tube diameter due to the surface tension? Okay, so all you need to do is to just simply write this capillary rise equation. Here the question says what tube diameter is needed if the water level in the tube is to rise 1 tube diameter. That means H should be equal to 2R. And since it's killing tube, that means theta is equal to 0, cosine theta will be 1. Instead of H here, I just simply write 2R equal to 2 sigma divided by rho g R, right? And then you can then rearrange this equation, express R as a function of sigma and rho g. That will R will be equal to square root of sigma divided by rho g. We know the sigma for water. Okay, and we know the density of water, we know the gravity, therefore the radius will be equal to 3 millimeter, and the question is about the tube diameter, which will be 2 times 3 equal to 6 millimeter. I hope you found this video helpful. Thank you.